Welcome to Ask and Learn.
We want to sketch the curve y is equal to x over the square root of x squared plus 1. So in this chapter, they give us this laundry list of steps that we should follow. So let's go ahead and just follow it. So the first thing they tell us to look for is our domain. Well, since this is a rational function, we need to make sure our denominator never equals 0. Well, x squared plus 1 will never equal to 0. It will always be greater than or equal to 1. And for the square root, we need to make sure the inside is going to be strictly greater than 0. So we could really just say that we need to ensure that x squared plus 1 is strictly larger than 0, which in this case it is. So our domain is just going to be all real numbers, or negative infinity to infinity. The next thing they tell us to look for is our intercepts. So let's find our x-intercepts first. So remember, x-intercept is where the function is equal to 0. So 0 is equal to x over x squared plus 1 square rooted. And this would be only where the numerator is equal to 0. So 0 is equal to x would be where our x-intercept occurred. And it just so happens that when x is equal to 0, it also tells us our y-intercept. So our origin will be our only intercept in this case. Next, we can go ahead and look at the symmetry of our function. So functions like this normally aren't known for being periodic, but we can at least check if f of negative x will give us it being even or odd, and we can use the symmetry about the y-axis or the origin. So plug it in, negative x will give us negative x in the numerator, and negative x squared, which would just be x squared plus 1, and this here is equal to negative f of x. So we know we have an odd function, so odd, and that means symmetry about origin. So whatever happens on the right of the function, we will know will happen on the left. We just need to make all the values negative. And on the right, I mean to the right of x is equal to 0. All right, so let's go ahead and look at the symmetry, or the asymptotes now, of our function. So we're not going to have any vertical asymptotes due to the fact that our denominator will never equal to 0, but we will have in behavior for it going to infinity and negative infinity. So this might take a little bit of space, so let's do this on a new page. So we want to look at the limit as x approaches infinity of x over the square root of x squared plus 1. Now, since this is essentially a rational function, remember to find the end behavior of this, what we would do is identify our largest power in the numerator and denominator, and then just divide the top and bottom by that. So in the numerator, it's x. In the denominator, it's x squared, but we're square rooting it, so it would also be x in the denominator. So overall, the largest power is x, so we want to divide the top and bottom by, or multiply the top and bottom by 1 over x. So doing that, we'd get 1 in our numerator, and in the denominator, when I bring in that 1 over x into the square root, I'm going to need to square it. So that's going to give that this here is 1 plus 1 over x squared. And now we can go ahead and apply the limit as x goes to infinity. And so this term here goes to 0. So we would just have 1 over the square root of 1, which is 1. Now, we could go ahead and do the exact same thing that we just did for negative infinity. I'm just going to say f of x. But if we go ahead and use the fact that this is an odd function, well, that means we can rewrite this as the limit as x approaches infinity of negative f of x. And this is since odd function. And now let's factor out that negative, and we get negative limit as x approaches infinity of f of x, which will be just negative 1. So you could go through the same steps as what we did before, but you'd have to remember when we pull in this bottom one, we'll have to multiply by a negative sign, or we would just switch the signs like we did before. But I think doing it this way would be a little bit easier. So we now know our end behavior will be 1 and negative 1. All right, so let's go ahead and write that over here. So we have the limit as x approaches infinity of f of x is going to be 1, and the limit as x approaches negative infinity of f of x is going to be equal to negative 1. Now, the next steps, 5 and 6, were to look for intervals where the function increase and decrease, and we also want to use that information to find out if we have any local maxes or mins. So we'll need to find what y prime is equal to. So let's do that on another page again. So again, y is equal to x over x squared plus 1. So to take the derivative of this, we can use the quotient rule. So y prime is going to equal to, so it's low d high minus high d low all over the square of what's below. So dx of what we have in the numerator minus them in the opposite order. And x squared plus 1 square rooted all over the denominator squared. So that would be x squared plus 1, and we would normally have absolute value on the outside here, but x squared plus 1 is always going to be larger than 1, so we don't need to worry about that. All right. And so now the derivative of x is just going to be 1. The derivative of square root of x squared plus 1, well, we'll need to use power rule and chain rule. So first for the power rule, we'll get 1/2 x squared plus 1 to the negative 1/2 power, and then the derivative on the inside is going to be 2x. Now, just to save some time, I did this algebra earlier, and this should give us 1 over x squared plus 1 to the 3/2 power. Now, you might notice that this here is strictly larger than 0 for all values, since, well, it can never equal to 0 since our numerator is just 1, and our denominator will also always be larger than 0 since x squared plus 1 is always larger than 1. So we have no critical values for this, and we know the function is always increasing. So let's go ahead and write that down. So y prime was 1 over x squared plus 1 to the 3/2 power. And we know that the function is increasing when y prime is strictly larger than 0, which happens to be just for all real numbers. And then that tells us our function is decreasing when y prime is less than 0, never. And again, we'll have no critical values since that function never is equal to 0, and y prime is not undefined anywhere. All right. The next thing we want to do is to check for not asymptotes, but concavity of the function and any inflection points we may have. So we're going to need to know what y double prime is. So let's go ahead and do that. So this time I'm going to first rewrite our function here as x squared plus 1 to the negative 3/2 power. That way we don't need to use quotient rule, and we can just use power and chain rule. So y double prime is going to equal to negative 3/2 x squared plus 1 now to the negative 5/2 power, and then we take the derivative on the inside, which is going to be 2x. So let's just rewrite this really quickly, and doing that will give negative 1 or negative 3 x. Oh, actually, I was looking at the wrong thing. So this here should be negative 3x over x squared plus 1 to the 5 halves. Now, this function here can equal to 0, and it will equal 0 when x is equal to 0, since we would set the numerator equal to 0. So we'll go ahead and use this as a possible point of inflection. All right, so we have y double prime was negative 3x over x squared plus 1 to the 5 halves power. And we know that our function is going to be concave up. So y double prime strictly larger than 0, which is concave up, on the interval 0 to infinity. And the function is going to be concave down, or y double prime is less than 0, on negative infinity to 0. So we said our possible point of inflection is x is equal to 0. So to the left of x is equal to 0, the function is going to be concave down. And to the right of 0, the function is going to be concave up. So actually, these intervals here should actually be opposite. I wrote them down incorrectly, it seems. Just because the denominator is always going to be bigger than 0. So the only thing that really matters is when negative x is bigger than 0 and less than 0. So this should actually be, I'm glad I caught that the function is concave up on negative infinity to 0 and concave down from 0 to infinity. Here. So it's concave down to the right of 0 and concave up to the left of 0. So it's still going to be inflection point, but we'll need to know this concavity, or the concavity won't really make much sense when we actually go to sketch it. All right, so we know our intercept was at 0, 0. And we know we have asymptotes at y is equal to 1 and y is equal to negative 1. Y is equal to 1, y is equal to negative 1. And we have no local maxes or mins, but we do know we have an inflection point at x is equal to 0. All right, so let's start on the right side, and then we can use the symmetry of our function to just draw it pretty much in the opposite manner, going towards negative infinity. All right, so we know the function needs to be concave down to the right of 0, and it should always be increasing. So it'll look something kind of like this, but we have a horizontal asymptote at y is equal to 1, so we need to get slowly closer to it. And since we know this is an odd function, we have symmetry about the origin, so we'll just draw it in the exact opposite manner, going into the other quadrant, like so. And we see it's concave up still, and it would still be increasing from negative infinity to 0, so that works out. So you could maybe go in and draw 1 or 2 different values here, but as long as we show that we have the change in concavity at x is equal to 0, since we see to the left it's concave up and to the right it's concave down, and it's always increasing, I think that's all we really need to show in this one. So I would stop here.